Anti-topological spaces. Anti-topological spaces have been defined by Sahin, Kargin and Yucel in 2021. These structures have been introduced together with so-called neutral topological spaces, which are connected with neutrosophic sets of Smaragdacha. The authors studied some basic properties of these two classes and the most striking relationships between them. In this video, we shall concentrate only on anti-topologies, not on neutral topologies. Recall that in case of topological spaces, we assume that our family tau of subsets is closed under certain operations, namely finite intersections and arbitrary unions. Moreover, we expect that both empty set and X belong to tau. As we know, there are also weaker structures like generalized topologies, so-called supratopologies, where we have closure only under arbitrary unions, not necessarily under finite intersections. We have so-called infratopologies, where we have finite intersections but not necessarily any unions. And we have minimal structures, which are characterized by the fact that empty set and the whole universe belong to such family, and so on. We have also weak structures and generalized weak structures. But anti-topological approach reverses these assumptions in some sense, namely this assumption about closure under certain operation. Why is that so? Well, let X be a non-empty universe and T be a collection of subsets of X. Non-empty collection. We say that Xt is an anti-topological space if the following conditions are satisfied. Empty set and X, they do not belong to T, and for any natural number n, if we have a finite collection of subsets taken from T, as it's written here, then their intersection is not in T. And for any collection, for any family AI, finite or infinite or maybe even uncountable, such that AI is in T for each I in J, their union is not in T. Well, to make this definition consistent, we must exclude trivial cases, of course, that is when all the sets in question, all the sets here and all the sets here are identical. Of course, intersection of this set with itself gives us the same set, and the same with union, yes. Some examples. Consider, this is taken from the original paper of Sahin and et al. Consider this universe, 1, 2, 3, 4, 4 elements, and this anti-topology. It consists of these three subsets, 1, 2, 2, 3, and 3, 4. One may easily calculate all the possible intersections, non-trivial intersections, and check that they do not belong to this family. This same with unions. 1, 2, union with 2, 3 gives us 1, 2, 3. It does not belong to T. 1, 2 plus 3, 4 gives us the whole universe, which is not in T. And in this case, we get 2, 3, 4, which is not in T. Some other examples invented by us, by me. This universe A, B, C, D, E, 5 elements, and this anti-topology A, B, C, D, E. Or something more complex, we have the set of natural numbers as our universe, and assume that T consists only of these subsets, of these finite subsets of X, which have cardinality K, where K is certain number. So in any particular case, we would have K equal to 5, let's say, or K equal to 80 or 100 or something. Now, if we have two sets of this particular cardinality K, which are different, then their union has cardinality greater than K, this is in here, and their intersection has cardinality lesser than K. So their union does not belong to T, and their intersection does not belong to T. And of course, empty set and the whole universe do not belong to T. Again, consider the set of real numbers and assume that T consists only of these closed intervals which have length y, where y is certain number. so they are of the length 1 or 12, yes, we should fix it. Now we will have two subsets taken from T, which are different, two intervals of this kind, which have the same length. Then their union has length greater than y, or it's not an interval at all, but a union of intervals like 0, 1 plus 5, 7. And their intersection has length lesser than y. Moreover, the intersection can be empty, or it may consist of one point. And clearly, empty set and the whole universe do not belong to T. So these are some examples of anti-topologies. Let us call the elements of T, this is our own invention now here, anti-open sets. And we may easily define an interior-like operation. We may define anti-interior of any set A as the union of all anti-open sets contained in A. For example, take T from example 1. It was here, as you can see. And consider 1, 2, 3 as our set A. Then its anti-interior consists of 1, 2 plus 2, 3. It's 1, 2, 3. It's identical with A. Now take T from example 2. It was here. A, B, C, D, E. And consider A, B, C. A, B, C. And the union of all anti-open sets contained in ABC is just AB plus nothing, it's just AB. So anti-interior of A is AB. Clearly, this anti-interior is never anti-open if it is formed by the union of at least two different anti-open sets. Yes, because any union of two different anti-open sets is not anti-open, it's beyond the anti-topology. Moreover, we may predict some of the basic properties of anti-interior, like monotonicity, like the fact that anti-interior is contained in the set itself. Yes, if the set is anti-open, then it's identical with its anti-interior. If A is contained in B, then, well, this is the monotonicity property, then anti-interior of A is contained in anti-interior of B. Idempotence is here, and this property. X belongs to anti-interior of A, even only if there exists anti-open sets such that X belongs to these anti-open sets contained in A. And these properties, why they say that they are that we may predict them, because these properties are true for any interior-like operation. Interior-like, it means defined as the union of our open or minimal open or generalized open or anti-open sets. Yes. So for any interior-like operation defined with respect to some non-empty subfamily of X. And one can check this fact in the paper by Avila and Molina on generalized weak structures. And finally, we think that it would be valuable to continue the research on anti-topological spaces. What is remarkable is the fact that each anti-topological space T is connected with topological space tau, consisting of the empty set, the whole universe, and all the unions and all the finite intersections of elements of T. We may also consider tau minus T. So that's all for today. This is the bibliography. Here you have the paper about generalized weak structures. And here you have this original paper by Turkish authors about anti-topological spaces and neutral topological spaces. Thank you very much.